What?
Oh, yeah.
So, we were late last time. My grandma did. I feel your pain. So I was like, fuck it.
What I have, I should have had.
I don't think we can do that. Yeah, I just need to write it down.
1:15. That's
Yeah.
And plus one or minus each. Wow, it's like, is it mostly bad or is it just questions?
I really don't know.
sorority.
That's really the yes, general knowledge.
Alright, last day on chapter 5. It's been 2 weeks with control volumes. Quick announcements, if you didn't get your homework 4 back from me on Wednesday, drop by my office to pick up your graded homework. There was something else as well. Oh, I want to get a sense, how many of you have been going to been stopping in, once a week at least or so, and with tutor hours with Liam? Okay, so this has been have they been pretty useful? Has Liam been helpful?
Yeah.
Alright, good to hear. Awesome. Alright, so today we're going to be wrapping up chapter 5, just kind of putting it in context, doing 2 more example problems, and then motivating chapter 6, which we start next week. So far, chapter 5, what have we really done? Well, it was really kind of a natural extension from chapter 4. Remember, chapter 4 dealt with things like material derivative and field representations, and in chapter 5 we said, alright, how do we develop this into a way of applying conservation laws to volumes in space rather than to sets of particles. So we developed this control volume representation of these conservation laws, like conservation of mass, conservation of linear momentum. Those are the 2 we've been working with. Right. Additionally, there are other conservation laws that we see regularly in physics and in fluids, namely conservation of angular momentum, also called moment of momentum, and then the energy equation. We're not going to be covering these 2 explicitly, but I want to let you guys know you should read section 531 in the book. It's a quick subsection in the book, just so you get a sense of how the energy equation comes into play. So since we're not doing, going over these really rigorously in lecture, let me just do a quick summary, the idea here, so you're not completely in the dark. So conservation of angular momentum, it's a pretty natural extension from linear momentum, right? Here's our conservation law for linear momentum. This is the one we've been using. Sum of the forces is equal to rate of change of momentum in a control volume plus the flux of momentum across its control surfaces. However, how do you usually write a force due to a moment, or a moment due to a force, right? If you have a force being applied, if this is your coordinate system, and you have a force occurring on something out here. Let's say you have a solid body, and you're applying a force out here. The way you compute the moment about this point is, of course, you say, here's some vector r that tells you the position of the application of the force, and then the moment is, well, it's written up there, is cross product R by F. And remember that the moment here is also a vector itself that's perpendicular to both of these, so it'll be sticking out of the board at us. So if we go ahead and apply this, if we put an R cross in front of every term in our linear momentum equation, what we get is the conservation of momentum. So the sum of all of these little moments induced by forces can now be written as the sum of velocity, or the rate of change of velocity moments inside the control volume plus the flux of these velocity moments across the control surfaces. And what this looks like more familiarly in rigid body dynamics and such is that the sum of all the torques or moments on a body is equal to the rate of change of its angular momentum, right? So things like if you have a torsional pendulum or an engine, crankshaft or something, you apply a certain force, you have to calculate its moment of inertia, and you can then back out the rate of change of its angular momentum. Same thing with fluids, and so it comes in to play usually when dealing with rotating problems, things like pumps, turbines. I think there are a couple of examples in the book dealing with like rotating sprinkler heads. Anytime that you're dealing with shafting and applying torque into a system. The other one is the energy equation, and you guys have all had at least first level thermo, right? At this point. All right, so you've all seen the energy equation before, I take it. The idea being that, maybe not in this form, the idea that the rate of change of energy contained in the system is the sum of the rate of heat transfer into the system plus the rate of mechanical work into the system. And so by the same application of Reynolds transport theorem, we end up stating this in a conservation law on a control volume, shown here, where, again, if E is our specific energy, then the rate of change of the system energy can be written as time rate of change of control volume energy plus the flux rate of energy across the control surfaces. Again, give 531 a read so that you have a more fleshed out understanding of this, but it's relatively straightforward. Okay, so I just wanted to kind of sketch out what the conservation laws that we didn't deal with explicitly are in this class. But what we're going to spend the last day of, well, actually, let me skip over this for right now. So, why is Chapter 5, why is the stuff we've learned so far useful to us? Well, the control volume approach, as I've said repeatedly, is great because it allows us to kind of zoom out of the problem. We don't need to worry about the details of the flow. For many of the problems we've been looking at, especially once they're steady, you can just look at the inlet and outlet and kind of know what the net effects are going on inside some black box we've created. So good examples are things like water jet pumps on boats. If you're looking at a jet boat, if you look at the inlet and you look at the outlet, you see the size of the inlet, the size of the outlet, you measure the velocity, so you can calculate the thrust being generated. Simple. You don't need to measure pressures, you don't need to evaluate the impeller performance in CFD. All you need to do is know what's going in, what's coming out, and what's the difference between those two values in terms of linear momentum. All right, so it's really, really useful, a very practical skill. And it allows us to solve a lot of complex problems. Things like tipping blocks, volcanic eruptions, or thrust created by jet pumps. Okay. The problem with control volume analysis is the same as its strength. By really zooming out, we also lose, what we gain in simplicity, we lose in granularity. So if we want to know the details of what's happening in the flow inside a control volume, we just can't do that using control volume analysis usually. right? So lots of detail, or lots of situations where we're actually very concerned with the details of the flow. For example, let's say we're looking at a pipe here, right? If you take a slice through this end and a slice through this end, just look at the velocity profiles going in and out. You could calculate what's the difference in linear momentum, and therefore what's the total force, or the rate of change in linear momentum, and therefore what's the total drag force of the plate, or the pipe walls on the fluid. However, you're not going to capture the development of this viscous boundary layer. You're not going to be able to see that happening in real time, or figure out like what the character of the flow is at any point between the inlet and outlet. Things like the detailed, oh come on. No, that video doesn't want to play. Alright, things like the details of flow around airfoil sections. I showed that if you draw a box around this, and you make some assumptions about the flow, right, you can assume certain things about the angular deflection of the flow by an airfoil. You can actually calculate the lift at a given speed. But the way in which we, the details that lead to those assumptions, things like the way it detaches here from the trailing edge, if you end up with stall on the airfoil and such, you just can't get those with control volume analysis, because once again, you have put a big blinder over the details of the problem and you're only looking at the edges. Another example is things like flow around bridge pilings or other circular objects. How many of you have been, any of you got those old kind of coat hanger style antennas on your car? You ever been driving down the freeway and you hit a certain speed where the thing just goes nuts, starts going back and forth?
That's
No.
like 10 miles an hour.
10 miles an hour? Alright, that's so that's an example of what's called vortex induced vibration. And Professor Bernitzis loves this stuff, so you're going to see a lot of it in 321. If it won't play either. Oh no. Hold on, this one's cool. I'm going to find it. Alright, vortex-induced vibration, and vortex shedding. So it is with certain types of bodies, as flow goes across them, you get these, you'll get a vortex building up, and then it'll detach and destabilize another vortex, and which will then build up and detach and destabilize another vortex, and you get this alternating back and forth shedding of vortices. And this is a specific phenomenon called von Karman vortex shedding. And it's a really cool thing. It's a very reproducible phenomenon. I've seen this in my own research. But one of the neat things about this is if you're someone like Professor Bernitzis, you can make this rod here, you can attach it to a spring, right? And you can tune that spring and the mass and the damping of the system such that the frequency at which these vortices are being shed matches the resonant frequency of your system. And it'll drive the thing to start moving with large amplitudes, and you attach that to some sort of power converter or generator, you can use this thing to create electricity, right? So lots of really cool flow phenomenon that we just don't have the level of detail with control volume analysis necessary to analyze them in depth. Now there's a caveat here. Have any of you dabbled in any CFD, tried messing around with Fluent or CFX or anything before? No? Alright. Well, CFD, the big, I don't know, kind of the elephant in the room sometimes. People are like, yeah, CFD, it's cool, but there's a reason they also call it coloring for dollars sometimes. It's a method that allows you to approximate details about a fluid field. But the way it does that is by taking, for example, it'll take a flow domain like this, and it'll draw a mesh on it. Right? It'll divide it into a bunch of little tiny pieces, each of which it treats as a control volume. And it applies some of the same conservation laws that we've been using on large control volumes, just on a much smaller scale. So this is one of the ways they get around this sort of problem, where they say, all right, the real detailed equations of motion for a fluid, Navier-Stokes equations, which we'll be dealing with in the next chapter, are really complicated. They're hard to get general solutions for. So instead, we're going to use control volume analysis and just make the control volumes really tiny so that that loss of detail is only inside of really small volumes. And that's a pretty good way of doing it, but the problem is that with CFD, if your problems get very large, spatially speaking, and you're still interested in seeing details of the flow that are small, then you start to build up really large systems. So you'll end up with, I think I showed an example in the first day of class, with apparently my computer won't play any videos. But problems like this, simulated in CFD, you can quickly end up with hundreds of thousands to millions to, in the case of this simulation over here, 380 million separate control volumes that you have to solve, conservation laws for independently. And moreover, you have this relationship where you say what's flowing out of one control volume has to flow into the next one, so you have these additional conservation constraints. And so that's kind of fun. That's fundamentally how CFD works. There's a lot more to it, and I'm not an expert in CFD by any means, but kind of frames the problem. So, starting on Monday, we're going to be dealing with a much finer level of detail in the physics of flow. Okay, and the idea is by the end of chapter 6, we shall have learned sort of the basic physical laws that allow us to describe all of these details with a greater level of mathematical precision. We're not going to have to zoom out and say, hey, control volume analysis. We can instead say, here are the actual equations that govern what's happening on a very, very small, at different points in space. What we might not be able to do is solve all those equations. In fact, we'll see that the governing equations for fluid motion, the equivalent of F equals ma applied to fluid continua, is actually, it's an open research question, right? There's no solution for the so-called Navier-Stokes equations. It's one of these grand challenge questions, right? I think if you come up with a closed form solution for the Navier-Stokes equations that govern fluid motion, it'll net you something like $1 or $10 million prize. There's like a bounty on figuring out what the solution is. So that's what we're getting into in chapter 6, going after the $1 million. All right, so with the remainder of class time, we're going to try to hammer out a couple more examples. So we've been showing this video of like jets branded block, and the block eventually tips over. We've seen it probably a dozen times in the last 2 weeks. But let's actually figure out, what's going on here using a control volume analysis. So if we make an assumption about our block, let's say, let's draw this in 2 dimensions, where we've got a block of width W, height H, and then we've got a stream of water spraying in and impacting the block. The question that we're seeking to answer here is, for the right page, what is the actual flow rate required in this jet the volumetric flow rate? What is the volumetric flow rate Q required to tip this block over? Okay, so things that we're given here, I'm going to write up. So our givens for this problem are, we know the area of the jet, we know the width, height, and we'll let L, script L, denote the width of the block going into the board. And we know the weight of the block. So what we're trying to find Q to tip block over. Alright, and assumptions that we're allowed to make here. I'll just give some to you. We may assume that rho is constant, the flow is steady, velocity is uniform across the jet, and all right, so let me figure this out. So first step in solving this is going to be what? What's step one? First action. Control volume? Control volume, that's exactly. So, let's go ahead and define our control volume to be this red area here. And let's go ahead and identify places where we have flows of interest, right? We've got inflow occurring right here, right? We'll say this is, V1, and then some of this water is turning and coming back out. We'll say this here is V2. So we have control surface 2, control surface 1, and then the normal on the surface is going to be pointing out, right? All right, next step here is going to be to draw three body diagrams of the control volume and of the block, right? We're interested in both of them because we need to figure out what forces and moments on the block will induce it to fall over. Okay. So why? So all right. What else do we have? So what other forces are we going to have acting on the control volume? Call them out. Force of the water? Well, let's see. Are you talking about something that's going on over here? Okay, is that going to be semantics maybe, but is this force of the water or is it force of the block on the water? Right.
So do you ask like what
So-
forces are acting on the control volume?
What forces are acting on the control volume?
Maybe the plates force.
Right? Okay, exactly. So let's go ahead and call this X. Once again, we're probably not, like we know it's going to be pointing this direction, but we're going to define it positive and let the sign come out as part of the solution. So of X, go ahead and say maybe it has a vertical component as well. Yes, we are going to have pressure acting on this. However, color this one. It's atmospheric pressure, and so just like in the case with the jet acting on the plate, we kind of know all ahead of time. Well, atmospheric pressure is not going to push this one way or the other. So we could make this more complicated by calculating all the pressure forces. You're going to end up with some pressure force on the control volume that isn't balanced on this side, but will be balanced on this side. So it's really it's a choice of how detailed you want to get. But for now, let's make the assumption that we're dealing in atmospheric pressure measured in gauge pressure. So we can just say 0 and no resultant force due to pressure. All right. Probably, yep. We're also going to have weight of the water in the control volume, right? All right, how about the block here? We've got
Normal force?
down here,
To the right? What's
Yeah.
it?
like that.
Yeah.
Good. Yes. And then over here we're going to have force of the water jet on the block. Right? Okay, so as Joe already pointed out, if we have, let's go ahead and define this point here as point A. At the moment, this block is about to tip over, sort of the constraint on the problem. The normal force is going to be acting right at this corner. Okay. All right, so now let's look at this control volume in a little more detail. we have our normal pointing out, we have V1 going in, we have V2 coming out. We're going to simplify this a little bit more even by saying this little bit of spray here that's returning back outside the control volume. If you were to look at the video, which won't play very carefully, what you would see is that the velocity and the thickness of this spray sheet is pretty minimal. That's because it fans out kind of in a large three-dimensional circular puddle that kind of creeps across the control surface. And so we're going to say that the actual velocity at which this is coming back out is approximately 0. Okay. So let's add that to our list of assumptions. 2 is approximately 0. And let's also go ahead and make the assumption here that this jet is acting at the center of the block. And so we'll say this isn't exactly true, right? This is going to induce some pressure field on the block that probably causes the resultant force to be somewhere other than the center of the jet. But for right now, for simplicity, let's go ahead and assume that this is being applied at half of the height of the block. Alright, so our governing equations. Control volume. Let's say our limit on static equilibrium for the block here. Sum of the moments about A is going to be equal to 0, right? If we this is the at the equilibrium tipping point when the normal force is being applied through the rightmost point it can be. If the sum of the moments is equal to 0 there, that means it's balanced on this corner. So that's the division between it standing upright stably and it, going timber. So we can write this out now as the weight of the block times the width of the block over 2, right? So the weight of the block is here. That's positive, isn't it? X, Y, and minus, what's the moment induced by the water jet here? Fx h over 2 to the 0, right? So from this, we get that the required force of the jet to tip the block over X is equal to the weight of the block times the width over the height, right? So here's governing equation number 1, and number 2 is going to come from conservation of linear momentum, right? So sum of forces in we're going to limit this to the x direction because I think it should be pretty clear that if we're assuming, I didn't say inviscid here. Inviscid. If there's no viscosity, then there can't be any vertical force between the block and the fluid. Right, so we don't need to worry about conservation of linear momentum in the y direction because it's not going to influence this side of the problem. So sum of the forces in x equal to rate of change, control volume, God, I am excited to move on to differential flow analysis, shorter equations. V plus control surface V rho dot n dA. All right, cancellations. Got steady flow, right? That goes out the window. And in terms of control surface integrals, we really only have one area of interest, right? We have two areas where flow is either entering or leaving, but we've made the assumption here that the velocity is approximately 0. So we've also made the assumption that the flow is uniform, we have constant density. So what this turns into is that this turns into V1. I want this to be U because we're doing it in the x direction. U rho V1 dot N1 times area 1, right? So V1 dot N1. What do we know about this? Well, just point in opposite directions, right? So it's going to be negative magnitude of V1. If V1 is equal to U in the x direction here, we can simply say that V1 is equal to Ui plus 0j. So its magnitude is equal to U, which we'll just say is equal to the jet velocity. All right, we'll change the notation here a little bit. So that allows us to substitute Vj here and negative Vj here. So we end up with negative Vj squared rho A. Okay, so we've got the force of the block acting on the fluid, negative direction. That makes sense? Yeah? But we've got the required force of the fluid acting on the block in order to tip it over here. So let's go ahead and set those equal to one another. So we've got WB, W over H, equal to negative. Wait a moment here. I've got an inconsistent negative sign here somewhere. That's because I used the same notation here. Let's go ahead and call this force here Rx. Right? Rx. And what we know here is that if we have a value for f of x, Rx is going to be negative fx, right? Because it's a reaction force and a reaction force. So at this interface, force equal and opposite reaction. So we end up with a negative WB ux is equal to negative Vj squared rho A. So what we're looking for here is Q, right? What do we need in order to get Q? We need V and we need area. We have area, right? It's one of the givens, the area of the jet. And so we need to solve for velocity here. So go ahead and cancel out our negatives. What we end up getting is that Vj is equal to square root of the weight of the block area of jet times W over H. So then Q is equal to Vj Aj is equal to WB Aj over rho W over H. Let's go ahead and make sure that this is dimensionally consistent. We have here, let's see, weight over height, or width over height, dimensions, right? Dimensionless. Area, length squared, so we've got a square root of length squared. Weight is going to be mass, length, to the negative 2, and then rho is just mass, length, to the negative 3, right? So we have mass, or we have length negative 3, up here we have length squared times length, so those two things cancel one another out. What's not making sense here now? Oh, because those don't cancel out. Like negative 3, those end up coming up top, and what we end up with is then length to the 6th time negative 2, and these lengths cancel out. Nope, sorry, the masses cancel out, that's what I mean. And so taking the square root of these, we divide each of these powers by 2, and we end up with length cubed per time. So meters cubed per second or something, which is a correct dimension for volumetric flow rate. Alright, so there's how to calculate the required flow rate to tip over a block. Question though, what if we modified the problem? Let's say instead of the way it was drawn, what if instead we carved out a scoop on the front here so that the jet got redirected back out. What do you think would happen to our value Q? Would it change, go up, go down? We required, well, you think that we would require more flow to tip it over? Or?
That's a guess, but
Alright, well what's happening here? If we use the same control volume, what we've got now is, let's say we have V1 is equal to Vj I, and V2 is equal to negative Vj times I. So velocity going in is the same as the velocity coming out. Let's say that we have same jet area. Essentially the jet has just been turned around and shot back out where the control surface it came from. Alright, if we were to write out very roughly, kind of skipping some steps, our conservation of linear momentum, we would get forces x is equal to steady flow, so nothing there, negative Q in times rho V J plus Q out rho negative Vj, giving us negative 2Q, if we're saying Q in is equal to Q out, right? Negative 2Q rho Vj. Right? This is compared to before we had 1 rho Vj. Yeah? So in other words, if we're assuming that the force is still, that the force created is going to be twice as great in this case, because now instead of just stopping the linear momentum coming into the system, you're flipping the sign and doubling the actual change in linear momentum. Right? It's the same as saying, you assign this some value. You said this is 5 kilograms meters per second coming in, instead of saying nothing leaving, so it goes from negative 5 kilogram meters per second to 0, and now it goes from 5 to negative 5. So your delta there is greater by a factor of 2. And so if we assume that the point at which the force acting on this remains at h/2, which is a very liberal assumption, but we'll deal with it for now, then what we're going to end up getting is that the required Q to tip the block over is going to be 1/2. Okay? Okay, any questions about this example, or yeah, we don't really have time to start the next one. Any questions about the homework or any of the stuff from this chapter? You guys feel like you got a pretty good grasp on the control volume stuff that we've been doing, linear momentum, conservation of mass. Again, I encourage you to get familiar with the energy equation. I don't plan on throwing any energy equation curveballs in on you at midterm 2, but I can't promise anything. So, okay. Well, if that's if you guys don't have any questions, then we'll call it a day a few minutes early. The other example that we were going to do, I will try to post the example problem and the written solution to it up on the Canvas site, so you guys can glance through that.